Alright folks, I want to talk today about why it is that the weather is concentrated in the mountains. It's a really interesting thing, an important thing when we talk about exhumation. In other words, wearing down the mountains. Why is it the mountains are getting all the action? So if you look around the world, and I'll show you some examples, if you go on the leeward side, in other words the downwind side of any major mountain range, it's a virtual desert. So in the Andes, east of the Andes, it's a desert. Downwind of the Himalayas, parts of western North America, anywhere you go where there's any sort of mountain range, the mountains take all the weather. That's just a rule. And we talked about the fact that we call orogeny or orogenic mountain building. This is just an orogenic effect. It's orogenic rainfall, it's an orogenic rain shadow. There's a lot of words for it. But this is just a simple little snippet to go through what it is and why it is. And there's some important concepts to do here. If we look here, this is a picture from the Andes where we have the west is down and the east is up. And you can see all the green stuff is there. We get the peaks of the mountains, and to the east of here, up, going up, this area up here is desert. The Atacama Desert is one of the driest on earth. But the western side, the windward side of the Andes, is absolutely gorgeous. It's like a jungle. It takes all the rain. This is a really neat picture of Oregon. So there's the Cascade and the Sierra Nevada mountain range there. And on the west coast, up to the ocean, up to the mountain ranges, it's absolutely green and luscious. Eastern Oregon is a desert, absolute desert. So here's the deal. If we start with, let's say, a station and a number of different points, a number of things to keep in mind is that if we look at the pressure at station A, it's about 1,000, right? So 1 bar. So we go from 1 bar to 0.9 bars to 0.84 bars. That means up here we're 84% of the pressure that we have at sea level. With that, we can see that the temperature is also changing. That as we go up, it gets cooler. So the pressure decreases and it gets cooler. So these are the two things that you know. I'll show you some other information about this. But whatever we do, this is something to keep in mind. And another thing which is very important is the amount of water that can be dissolved in air is a function of temperature. So on the x-axis here we have the temperature, and on the y-axis we have saturation water vapor concentration, grams per kilogram. Very handy units there. And that simply means the amount of water you can dissolve before you'll saturate. So if we're up above this curve, we are raining, pouring rain. If we're below this, we are undersaturated. So the air has less water in it than it could have. So there's a term called relative humidity, and relative humidity simply means the amount of water you have dissolved, let's say at 20 degrees, let's say if you're at 5 at 20 degrees, the relative humidity is the amount you have in the air relative to the amount you would at saturation. And you can see this is about 30–40% relative humidity because it's this much out of a total you could have of this much. And it's roughly a third. Okay? For any given temperature, you can figure out the relative humidity simply by looking at a plot like this and seeing how much water you could have there. Another way to measure it is the dew point. The dew point is, for a given package of air, let's say we're at 10 grams per kilograms here at 30 degrees centigrade, the dew point is the temperature at which it will saturate. So simply the dew point of this package of air is 15 degrees centigrade. So those are two obvious ways that you can measure the amount of water in the air relative to what it could have, or the amount of water it has at a given temperature and how far you'd have to cool it before it then condenses water. It's really quite a simple concept, but bear in mind that hotter air can carry more water. So taking a package of air and cooling it will almost always bring on saturation. I think you all know that. if you're in a cold vehicle and you're breathing a lot and you're putting a lot of humidity into the air, when that air meets the inside window, the cold window, your windshield, it condenses water on it because it has reached its dew point at that temperature. This is an important concept to have, and it tells you a lot about what's going on here. And the only other thing you need to know is the ideal gas law, which you know, which says that PV equals nRT. That's saying that pressure times volume equals the number of moles times a constant that doesn't change, so you can forget about it, times temperature. Well, isn't that neat? We've got pressure on one side and temperature on the other, which means they go together. And the cool thing is, if you think about it, if you take a volume of gas and you measure it, it has a bunch of molecules that are hanging around inside it. You squash it up, the molecules get more squashed together, and the pressure changes. So that the pressure and then the temperature, when you heat it up, the temperature makes these go crazy, and then the pressure will go up as well. So this is low pressure, this is high pressure, but temperature has a lot to do with it as well. So when we look at air as we go up in elevation, that if we have 1 bar of pressure here at the surface, by the time we get up to pretty much mid-level of Mount Everest, so we're talking about 5 kilometers, 5,000 meters, 5,500 meters, right? This air is only something like 50%. When we go to the top of Everest, pushing 7,000 whatever it is, the air is only 40% of what it normally is, which is why most people need to take oxygen with them. When we get really high, it goes to almost nothing. If we go on a bigger scale, a measure of the average kinetic energy of the molecule in that substance is what we're looking at here, how fast the air molecules are moving. If we look down here in what we're in, the troposphere, we can see that we get a major decrease. Then we go through a level zone here, and then it actually comes back up in the stratosphere and back down as we go up way into the thermosphere. Up here it gets hot again, right, when we go up high. But we're thinking about this area where we live, where generally the pressure and the temperature both decrease together. Okay, so orographic precipitation. I called it orogenic. I should have called it orographic, but you know what I mean. Again, this is due to orogeny. I don't care what you call it, it has to do with mountain, the effect of mountain, where mountains and hills force moist air to rise. And the idea here is we take saturated air at a fairly high temperature and we decompress it up into the high levels where it's much cooler and the pressure is much lower, and we reach the dew point, so the rain comes out. Then we carry that air that's lost its moisture, and it's dry air, and when we're on the lee side of the mountain, there's no rain left to do. That's simply the orographic effect. My apologies for calling it orogenic, but I'm a geologist, right? So to me, this is orogenic. Okay, so adiabatic cooling of rising air. An adiabat is a package of air that we treat as a closed system. So we grab a bunch of air and we let it rise up again till it reaches its condensation level. So that is simply cooling a package of air until it reaches its dew point, and then at that point we have either clouds or rain or whatever. Okay, so that was the orographic or orogenic rain shadow effect, as told to you by a geologist. But for everything else we think about, we want to know, why is it that the mountains take all the weathering? We talk about CO2 weathering out of the atmosphere. It's because the rain falls in the mountains. When there's more CO2 in the atmosphere, you have more carbonic acid to attack the rocks, to disintegrate the rocks and drive them downhill, down the mountains, in the rivers, to the streams, out into the oceans. That's the story in a nutshell. Thank you very much.